Yeah, there we go. The floor is yours.
Thank you very much, Eleni and Christian. Thanks for the invitation. I'm happy to be here and presenting. The title of my presentation is Digital Twinning of Structural Systems. And my focus is accounting for modeling errors and quantifying the uncertainties. So what is this digital twinning? I was telling Eleni and Christian earlier that basically had my model updating change the title to digital twinning. It's similar, so we use it in our community more model updating. Digital twinning, it has different representation, but basically if you have a numerical model of a physical system that can represent it accurately, it's called digital twinning. Digital twin. The process of calibrating it to represent the actual thing is model updating or digital twinning, which you need to have some sensors or measurements. And then you basically integrate that measurement with your model, and then it can represent your physical system better. And the systems that I focus on are mostly structural systems. So I show you a couple buildings, a footbridge, and a wind turbine. I cannot show you the actual wind turbine data. It is protected, but I will show you some numerical results. So the outline of my presentation is an intro to model updating, and then the Bayesian model updating that I work on. I call it hierarchical batch Bayesian inference. And then you can do it in the recursive Bayesian inference approach to a couple applications for each of them to highlight why they are interesting, at least to me. So why model updating? So model updating initially was very common for global structural health monitoring. It is an inverse problem. So basically, you know your measurements, you have an initial model, and then you want to tune your model to represent the data. And the model can be anything, basically. It can be a physics-based finite element, can be in the finite element code, can be in state space, can be a second-order differential equation, it can be a finite difference equation, whatever. Or it can be numerical, it can be an equation, polynomial, it can be a network, geometric, neural network. So once you calibrate it with sensor data, then the process is called model updating. So it is also recently referred to as digital twinning. And what is the SHM that I said? This is a part of that is basically assess the state of performance or health of a structural system. And the global SHM is when you have sparse measurements on a large structure and you don't have a prior information about the location of potential damage. This is in contrast with local methods, which they can more accurately localize and detect damage or performance, but you need to have a good prior knowledge about their location. So these SHM methods, they have been successful in certain applications, but there is still ways to go. So there are few sources of uncertainty. So one of them is measurement noise when you work with sensor data, and also the actual structure. They can be time varying, like they can be susceptible to changing ambient conditions and environmental conditions. So if you just do your inverse problem through an optimization, you get one answer, but you have no idea how good your answer is. So it's very important that you perform this process of digital twinning or model updating probabilistically. And also, even after you calibrate your digital twin, is not exactly the structure. It is a replica or wishful thinking of a structure. So there is modeling error. If you don't account for that, then whatever you represent, it can be overconfidence with your prediction. So it is important to account for modeling error as well if you can. So two sources that I discussed here. And basically my whole work is to quantify the uncertainties in estimations and try to quantify and account for modeling error. That's all I'm going to talk today. Now, if you want to quantify uncertainty, you have to do probabilistic approach. Two camps here, Bayesian camp and frequentist camp. You can do model updating, Bayesian approach and frequentist approach. I am in the class of Bayesian. So in general, Bayesian or epistemological concept of probability is that it measures the degree of belief. So you get information and then your belief gets more accurate. For example, if you flip a coin, let me get to the example later. And the frequentist is basically the probability is a measure of the proportion of outcomes. So flipping a coin again, the frequentist guy says, you know, you have a coin, forget about distribution of weight or like the surface it's gonna hit or like the force you apply to flip it. Just try it 1,000 times, count heads and tails, and that's my probability. Bayesian people say, oh, but you know, I can have data. You know, the person who flip it, they can flip it with a robot. They can measure exactly and repeat the sequence. They can measure the force on it. I can know the surface that it's gonna impact, so I can model it. And I can, if the more information you give, I say, oh, this goes with 95% heads. The frequentist guys say, you know what, this is too complex. You're fooling yourself by saying 95%. So there is this back and forth. The Bayesian people, the problem that is actually a valid criticism is that they can get overconfident. A lot of times we say 99% confidence interval. Well, in reality, it may be 50% confidence interval. So that's the challenge back and forth we go. But we get to that. So Bayesian inference is pretty much, you have a prior knowledge about your parameters of the model. Let's talk about the concept of model updating. So your model, you don't know the soil condition in the offshore wind turbine. And you don't know the nacelle assembly mass moment of inertia. GE wouldn't give it to you. Let's assume that. So you have a prior assumption for that. Then you have some measurements, you put some accelerometers, and then the prior knowledge gives you the prior probability distribution. The data gives you the likelihood, and you multiply these two together, it gives you your posterior. That's it. That's Bayesian inference. Now, if I want to do Bayesian model updating, I can collect all my data. Let's say I have 1 year of data monitoring of the wind turbine. So I collect 1 year of data. I have a prior. I use all the year-long data, and I do an updating using that equation. And then I get a posterior. That's called batch. Batch means all of them at the same time. Or I can say, you know what? I can't sit 1 year and wait for it. I want to see what is happening. So I say after every couple hours of data, I do an update. Or even after each sample of data, which is 1/100th of a second, I can do an update. It's up to us. You can do recursive once every 100th of a second. You can do it once a month. You can do it once a year. It's still recursive if you do it recursively. If you also look at the literature, like filtering, Kalman filtering is kind of a recursive batch recursion Bayesian inference. The bottom line is that both give you the exact same final answer. So the theory says that, you know, whatever you get from batch and whatever you get from recursive, at the end of the day, they are the same. But the recursive has more flexibility for some of the things we may be more interested in between. So for state estimation, for example, if you want to know the change in the input forces, or if you want to do virtual sensing, there are some techniques in the literature that they are only developed for recursive. And batch may also have some benefits if you want to get an overall modeling error or estimation uncertainty, because you have seen a lot. So let's go with batch. So I was a batch guy for a long time. So we went, tested stuff, collected data, came back to our office, we processed them. Now, we looked in the literature and we noticed that the hierarchical Bayesian is very suitable for structural engineering applications, civil engineering applications. Why? Because the sources of uncertainty that we saw in the structural system, for example, this is the data from a footbridge on campus at Tufts. I have years of data on that, decade of data on that. So one is measurement noise and identification error. So this type of uncertainty is perfect for classical Bayesian formulation. You get more data, this goes to zero. It's averaging, right? You assume measurement noise is Gaussian, you average more and more, it goes to zero. Fine, but there is something else. So if after a couple years, or even a few months, I look at the histogram of my identified natural frequencies, it has this shape. But if I plot it versus temperature, I see a trend. So it goes from 7 Hertz to 7.5 Hertz. This is not noise, there is something else. Some people consider this modeling error. They say, oh, you know what? This is like freezing of the concrete deck or freezing of the support. You know, below 0 Celsius, you have freezing. But most people don't model that. So you can consider, I call it like kind of an inherent uncertainty. There are a bunch of these things, like you change your traffic on the bridge, you change the wind speed, you temperature gradient, temperature, a lot of these. But this, they will not be reduced if you get more data. If anything, sometimes it gets larger because you haven't seen some seasons. So, but after you see enough data, it converges to a constant, not zero. The top part converges to zero, the bottom part does not converge to zero. So the point of hierarchical is that, oh, classical Bayesian, you update theta, the uncertainty of theta always goes to zero as you get more data. But in hierarchical, you assume that you have an underlying distribution that has a mean and covariance. I don't update my theta, I update my mean and covariance of theta. Theta, let's say, is stiffness of certain parameters. So this is the assumption. You update your mu and sigma of the parameter. And then the parameter has a fixed distribution. Let's skip the math to stick to 40 minutes. So this is the example. Let's say I have this building that the parameters actually change in time. So the distribution of these parameters are in the range of what we observed for the bridge. The buildings don't matter that much because there is not a lot of freezing and support change on all the floors. But for the sake of this example, assume that every parameter actually can change with a standard deviation that is written in front of it. So the stiffness of the first floor, the mean is 2000 units. And it can have a standard deviation of 100. Second floor, 1000, standard deviation of 50. Third floor, 1000, standard deviation of 20. So I sample 400 randomly from these combinations. And this is my 400 measurements. Let's say I monitor this building for 400 days. Each day I get one natural frequency. And then this is the histogram of the 400. Now, I can do my model updating using the first 5 days, the first 20 days, first 50 days, and first 400 days. And then I only update the mean and standard deviation of my parameters, which are stiffness. So you can see after 5 days, not the best for this one, but if you have 20 days for this specific distribution, which wasn't date dependent for us, it does a good job. So you see the exact is a solid line, and then anything after 20 set of data, I match it. So this is where how we design our hierarchical to work. So if you go and do a Bayesian update in classical Bayesian, of course it doesn't work. The more data you get, the uncertainty goes to zero. I call it classical. So if you get more data, you see it measures very accurately the optimal values of the parameters, but the uncertainty is so in classical Bayesian inference, estimation uncertainty is a myth, in my opinion, especially for large structures. So the uncertainty you use is, I don't know what it is. I know what it is, but we shouldn't call it. It's basically noise. You know, this works for some mechanical systems, some systems that they don't have variability. But when you have variability, this doesn't work anymore. So this is another graph. So in classical, so you see the blue dots, I have 6 plots. Let's look at the left ones. The blue plots are each measurement per day. Let's say for 100 days, I measure the response of the structure. They vary because that's what I assume. And that's what we have seen in the field. Like wind turbine, it varies even more. So the estimation is the red line. Does a good job, estimate the mean. And then plus minus 2 standard deviation is 95% interval. So you expect 95% of the dots fall inside the pink shade. That's why the frequentist guys don't like us, because we claim, oh, 95% sure everything is in that. And then you go and measure, it's more like 90% are outside. And then hierarchical basically knows the trick. It knows what is happening and it corrects for that. So if you know you have variability, I don't say that you always have it, but if you have, which you have for any civil structural system, then you have to do this. If it doesn't have variability, it's okay. Hierarchical is smart enough. It makes it very small, narrow, but the classical cannot do that. So, and the horizontal axis is how many data sets you get. So the more data sets you get in classical, the smaller it becomes. Few applications. This is a building in El Centro, California that was very, very damaged and was susceptible to the amplitude of excitation. So I want to show you that here in hierarchical, I can model the amplitude of excitation on the response of the building. So a linear structure response is a function of amplitude too. But this is nonlinear. This becomes nonlinear. The natural frequencies of a structure do change here. So this poor structure has been through enough. It's been through several earthquakes. It was raised for demolition, so we got access to it. And then we shook it hard. Let's see. So you guys hear the sound on my video or no?
No, I don't know if you want to share sound. We could probably do that, but we would need to
Let me run
reshare
it
your
again.
screen. Yeah, now.
You hear the sound. But this is a shaker in this corner. You see this thing rotating? So nobody was in the building. The camera is jumping up and down, so that's why the view is like that. But you see the shaking is where we are standing. Ground is shaking. And this is hard shaking. Now, forget about hard shaking, even smaller shaking. So these are called damage state. Let's focus on just one damage state. I haven't damaged anything in DS1. DS1 is pretty much the initial condition. It's a little different from DS0, but let's say DS1 is undamaged. The black dots are ambient vibration, natural frequency. Mode 1, around 2.4. Mode 2, about 3.3. It goes a little bit up and down, but look at when I excite it. When that shaker is rotating, it goes down to these triangles and rectangles and squares. And this is, and then it goes back up. So it's not damaged. If it was damaged for the shaking, it wouldn't go back up. This is damaged. You know, when there is permanent shift, this is a nonlinearity because the cracks are opening and closing, and this pore structure is in bad shape. Look at this guy. Again, I'm not saying this is true for all structures. Usually you see a little bit of that, but it's usually this much. But this structure is in bad shape. Anyway, so when we see that, we are like, what on earth is going on? And how can we do that? Let's discard full screen. These are the two modes that I'm talking about. So this is looking from the top, the 3 floors, pivoting about this point for mode 1 and pivoting about this point for mode 2. Then again, the structure had one side more stiff, so it was all torsional motion, which is good. The more torsion, the more information you can gain. If it's symmetric, you gain less. So we were lucky. So the natural frequencies in DS1, just DS1, ambient ones are all here. And then you do forced based on the amplitude of excitation. It changes. What we do here in hierarchical, we say, oh, you know, stiffness mean can be a function of amplitude of excitation. Kind of makes sense. So let's say that if your digital twinning or model updating is just optimization, you get the optimal values for your model parameters. If you do Bayesian, you get the optimal values and something called uncertainty, which we don't like it. If you do hierarchical, then we like it. We have the underlying distribution parameters of the parameter. And then if you know that your mean or stiffness changes with amplitude, you can model it. You can build the model inside your digital twinning. You can build a layer to that. And instead of updating mu, you update A and B. So you put these parameters and you update these guys. So that's better, hierarchical level 2. So if I do that, then I can say, oh, my model prediction is also a function of amplitude. So the gray ones are model prediction and the black ones are what we observe. So it does a good job. So just for the record, anything I show you on the slides, we did a good job. So I need to repeat that. If we didn't do a bad job, I don't put it in the presentation. But it depends on the structure. So some structures, you don't have this effect. You don't need to do this. But here, the ones I show you, it was very good to do this. And again, the acceleration predictions, you can get a confidence interval like 99 percentile or 95. I think this is 99 percentile. The pink one covers the measurement. Some of them, you want it to be very tight, but sometimes it's not very tight. But anyway, you see there is the exact, there is the mean of it and mean plus minus standard deviations. So overall, we liked it. Another hierarchical batch. These are batch. When we measure, we come home, and then we do the estimation. So this is a 10-story building. Here, I want to show you that most of the times, the modeling error that we assume 0 mean. So we just update covariance. Now I want to say, oh, sometimes you have a bias that you can estimate. If you estimate the bias, your predictions will be much tighter. I'll show that here. Again, these are real complicated structures. And we have a team of people working on that. So this is a team effort. So we have this building, 10-story, we put accelerometers in the corners and we get tons of data. So if you have just one set of measurements, you cannot do anything with it to quantify modeling error. You need more data, especially for hierarchical. You want to observe this variability in time. You have 1 hour of data, that's good, but again, not good for hierarchical to observe the variability. So this structure was again, so we get the structures they don't want. so we can do anything we want with them. So we break pieces of the structures to before they demolish. So again, I'm not talking about model updating for damage detection, which we did here. I'm just focusing on the effect of if you assume this error. So let's say your measurements are natural frequency and mode shapes, which is from vibration. They are features of vibration data. And then these errors, most of the time we assume zero mean and the covariance or variance. Zero mean and the covariance. Now I'm saying, oh, if you want to quantify your modeling error, it's good to do variance. You remember I said that we update the mean and covariance of the parameter. We also get the mean and covariance of the error, which is the leftover after you update. Now, this one makes the predictions better. Let me show you. So I update a couple parameters, Young's with stiffness of walls, stiffness of slabs. I do 3 cases. Zero mean error, most of the applications. Now, non-zero mean for one of them, non-zero mean for 2 of them. Now, how on earth I decided to do this one or that one? I'll show you. So first, when you do probabilistic prediction, there are 2 sources of uncertainty in hierarchical. One comes from this underlying distribution you assumed for parameters, which we update, mean and covariance. And one is we quantified the mean and covariance of our error, the modeling error. If you don't do this, your results are very bad. If you don't do this, your results are terribly bad. I mean the confidence intervals. So if you don't do any of them, you don't have confidence interval. You have just a point and you don't know uncertainty. If you do classical Bayesian, it's the same as you don't do any of them. Because it practically, this one goes to 0. Oh, you can consider this one in classical Bayesian actually. I take that back. Now this is the hierarchical that we did with zero mean for error. That's always what we do. We always assume zero mean. We did, the prediction is good. It contains, this is prediction, should contain the measurement. Natural frequency of mode 1 versus 2. Natural frequency of mode 1 versus mode 3 of this large structure. So I made an assumption that everybody knows what natural frequencies are, but they are features of the structure. And they are time invariant for linear structures. So it contains, very good. I'm happy about it. What I'm not happy about is why the gray dots are not tight. So if your prediction is not tight, it means that, oh, you say, oh, it can be here or it can be here. And then people say, oh, you know what? Forget about it. I could guess if it's here or here. But then I noticed that, oh, the black cloud and the gray cloud, they are different in F2 a little bit, 3.3 something to 3.4. But for F3, it's a lot. It's 4 versus 5. So I said, what if I have a correct mean for the error? So if I update mu3 for this case, so then this guy gets tight. Cool. Now this is a good prediction. I like it. And then if I update this guy as well, both of them are tight. So this is as good as we can get. But I didn't know it before I do it first case. I did first case, then I noticed I have bias. I said, okay, I update it. Usually we don't update bias depending on our modeling, but you can observe bias and then you say, oh, I update it. Third application, again, hierarchical. Let me check the time. Okay, I think I'm 30 minutes in. I have to rush a little bit. So I want to count for temperature and amplitude here. So this bridge that we have, this is Tufts campus. It gets cold in Boston, so things freeze. When it freezes, the performance is different. So if I look at my natural frequency of one of the modes, all of them are like that. So in general, you have this little bit of trend with temperature, the green one. I can let that go. And I have a little bit of trend for amplitude. I can let that go too, and kind of account for them in the big uncertainty I quantify. That's okay. I would do that if it wasn't for this part. This is bad. I cannot deal with that. If I don't deal with that, the overall uncertainty will be huge. And then you will not like my prediction because my confidence intervals are big. You know, a good prediction is that if you give someone a number and you say, okay, the confidence interval around this number is tight. So if I tell you my prediction is 10 and I say, oh, but the uncertainty means it's between minus infinity and plus infinity, then you don't like it. But if I say it's 10, 95% between 9.9 and 10.1, that's better. That's what I'm talking about. So anyway, I say, you know what? My mean of stiffness is the green line. Update the green line parameters. Update the blue line parameters and update the purple, magenta, sorry, purple, pink line. So instead of updating my mu, I update 1, 2, 3, 4, 5, 6 parameters. And for the uncertainty, I also say 7. So this becomes my hierarchical. So I am not updating my theta. Where's my line? So the classical will just update theta. The hierarchical says mean and variance of theta. That's good. But I can do better. I can say my mean, I don't update mean. I update parameters of this. I update these guys. So if you have these guys, then you have the mean. If you have the mean, you have theta. You get it? So I go deeper and deeper, then my results get better. How better? Again, confidence interval. If I just do hierarchical using modal parameters, I basically just update the mean. So the mean is constant. Then to compensate for this variability, I have a large coefficient of variation. If I account for the temperature, it just drops tremendously. So my predictions are much tighter. If I get amplitude of excitation, it gets a teeny bit better. All right, let's move on to recursive Bayesian. So let's say we are in a rush to get results as things move on. So we can do online prediction. Or if I have something in my state vector that I'm interested to get it along the way. So this is batch Bayesian. I have a prior, I have measurements, so I make my error. And here, I want to assume it has a mean and a covariance. Make my likelihood, get posterior. Okay, that was batch. Now, if I have sliding time windows, you know, my measurements are time history, so I can slide them to the next one. Now my posterior becomes my prior, and I repeat, get new measurements, go on. This becomes recursive Bayesian. Basically the same process, just using it in sliding windows or sliding points. Okay, so what I want to do here is, let's say that I have my finite element model, or however fancy model I have it in a first order finite difference or differential equation, and then I have my model parameters theta as a state. And not only I want to estimate theta, I want to quantify a time varying noise. So I want to estimate the mean of the noise, which is bias. So it's similar to the idea we had for hierarchical. and the covariance. So these are called adaptive recursive Bayesian. It has been done before. We have a new method for this guy. So this is a little bit novel. So again, Eleni's group has done a lot in adaptive filtering and recursive Bayesian model updating as well. This is similar to that, similar to like an EKF, but this one is the focus here. So in non-adaptive recursive Bayesian, you have a prior, you have your model prediction, you have measurements, you have an update based on the measurement, and go to your next window. That's it. Now, in the adaptive, so I use different terminology. Psi is the same as your state, but it can be augmented. So a lot of times when we work with this, we augment it maybe with the input force or whatever else you want. So psi is the same as your state. Whatever you want to estimate, you just bunch them together in this formulation that we have here in the state. And we assume a simple model for these ones. You can do better than that, but here for this case, just let's say that it's a simple random walk for your state moving. Now, the focus here is on adaptive. I not only want my state estimated, I also want, so I have a two-step thing I have a trick here to do this simultaneously. It needs a few more iterations, so it's more time consuming, but we want to estimate the mean and covariance of our error. So this includes not only noise, measurement noise, but also modeling error. Measurement noise may be very small, but the modeling errors are chunked here. I want to quantify that. And that's especially important when your modeling error or measurement noise is time variant. If it's not time variant, then what I'm talking about here, the left and right, they give you the same thing. If it's time variant, the left one wouldn't work. That's what I'm going to show. Let's say that, again, simple 3 degree of freedom, earthquake excitation, have some measurements, a little bit of noise here, but I assume my measurement noise is time variant. My mean and covariance, both are time variant. I'm trying to update some parameters of my model, like Menegoto, Pinto, Steele model parameters. And this is what I mean when it's time variant. So the actual mean for each of the parameters is changing in time. Now, this is simplified. Most of the times your mean is not a sine function, but again, this is just Mickey Mouse problem. So if you do non-adaptive, you assume a constant, doesn't work. This proposed method, it tries to track it. Same with covariance, especially covariance actually is changing. All right, so let's see what the results are. So the non-adaptive, of course, cannot do a good job estimating some of the parameters. The non-adaptive is red. Sometimes bad, sometimes good. But the interesting thing is the non-adaptive does a decent job to match your measurements. So if you match your measurements in any optimization, you shouldn't be too happy. You should be a little happy. That means your model matches the data, but it doesn't mean your model is good for prediction. I'm showing you right now in the next slide. So both of them match the data pretty well. The proposed approach, of course, can match it better, but still the red is decent. But when you go and do prediction, the non-measured response, like stress strain response history or other things, then the one that just matched the response and couldn't get the parameters of the model obviously does a bad job. So again, this is only true when you have your noise properties or modeling error properties time variant, which means every single structure when you look at long times. So within an hour, you probably don't have your modeling error changes. But within a season, Yes, you do. If you look at wind turbine, maybe within an hour it changes too. All right. Another application when we want to have a joint input parameter estimation, I cannot show you the, so we have measurements on this turbine and we have done this using the experimental data. Hopefully next time we have permission to share those, but just, this is a problem we want to estimate parameter of the model and the effective input force. Let me look at my time. I think I'm finished in time. This is the simulation. I have 3 cases. If I use just the acceleration data, it does a good job. No modeling error here. There is a little bit of gap, so a slow shift. If I use acceleration plus strain, it does a good job. And then the thing that I liked it here, at least in the numerical example, if we look at the acceleration, and then I look at the displacements that numerically integrated, but not the absolute values of them, the difference of the adjacent channels. The differences, they work well. And then I can get the wind load pretty accurately, as good as the strain. The only thing I cannot get, the wind load is not averaged around 0 in the real case. So this one will be averaged around 0. So it cannot give me the shift wherever the wind load was. I think the average of it may be negative something, but it wasn't 0. So it does a good job there, and it does the response predictions excellent. So this I liked to show. And I think that was my last slide. Yes, and then this work was done only by the students. I didn't do any of the analysis. So Ming, I think, contributed most to this presentation. Mansour contributed to the last part. Iman and Sina with the 2 building, especially the testing, was a lot of effort. And the support was from the National Science Foundation, the Bureau of Safety and Environmental Enforcement, Massachusetts Clean Energy Center, and National Offshore Wind Research and Development Consortium. I want to acknowledge the support that could help me to work with the students and collaborators: Andreas Stavridis, University of Buffalo; Kostas Papadimitriou, University of Thessaly; Hamed Ebrahimian, University of Nevada, Reno; and Eric Hines, Tufts University. We have had a lot of other collaborators that I don't put their names here, but they have been invaluable to help with that. And I couldn't resist to put this picture from yesterday. So yesterday I had to wake up at 3 a.m., go drive down to Rhode Island, get on the boat. It was a beautiful day. This is on top of one of the wind turbines on the helipad. And I couldn't resist to put the picture here. Thank you very much. We have a little bit of time, I think, for questions.
Correct. Thank you very much, Babak, also for the visual. I would like to thank you. We took a bit more time, but you did what resembles more of a webinar, because there was a lot of explanation in what you showed, which I think is appreciated by the audience. I would like to open the floor for questions by reminding everyone that you could unmute yourselves or raise your hand as Mike just did, so I'll give him the floor, or even write in the chat if you don't have a good sound and you're worried about expressing your question live. So Mike, you raise your hand, you can go first.
Hi, Lainey. Hi, Babak.
Hi.
Thanks so much. Yeah, Babak, thank you for the presentation. I wanted to get your opinion, as you go through imposing hierarchical Bayesian approaches, effectively, my way of looking at it is that you're imposing more structure on the model, the uncertainty model, which is, it's a good thing in general. I completely agree with you. And we're finding these approaches great, but you can go wrong, right? If you don't have a lot of data to see a trend, you could impose a model structure that itself is inducing an underlying bias. And I wondered if, how are you sure as you start to build models up with more and more detail, like you did, for example, where you were estimating the the freezing part of the structure, effect on natural frequency and so forth, that you aren't imposing something that itself is going to guide the inference in a negative way or bad way.
Yeah, thanks, Mike. This is an excellent question. So that is absolutely correct. The layers, so hierarchical is layered like an onion. The deeper you go in the layers, the more the danger of what you said is. The first layer, I just assumed I assumed a Gaussian distribution for my parameters. That's not very restrictive. You can't go wrong to assume a Gaussian, even if it's not Gaussian. It's still much better than not assuming it. Now, the second layer, I assumed a line, or I assumed like a curve or something to the form, but that's based on observations. So that is tricky. So if your observations are short and then you have a restrictive model, you're absolutely correct. And the way that the model compensates for that, if your model for mean is wrong, then your variance estimation will blow up. So your predictions will not be tight. So a good measure to check if what you did is good, see if your predictions are getting tighter. If they don't get tighter, it means that, oh, there was something based on something wrong with the assumptions. But that is absolutely correct. The more and more you go into these layers, there is more danger of when you want to predict for something that you have not seen, may not be following the same structure that the data you have seen provided you.
Yeah, thanks, Babak. That's a good point. Essentially, look for consistency and variance reduction. Those make sense.
Babak, maybe a question from my side. In what you present that resembles an extended Kalman filter, let's say, setup, I guess, would this be suited for an, let's say, real-time implementation, or does the hierarchical formulation essentially imply an offline updating process?
Is not, it can be online. It takes some time if you have a good PC, and we have some analytical solutions for these, then you can get them done.
Because a bit of my question there would be, I think you say this is almost equivalent to an extended filter, but I think that the fact that you're varying or modulating the noise, which is no longer Gaussian, would mean that we cannot, strictly speaking, we would not be able to use the filtering equations for updating, because
that's right. So these are different equations. They are not Kalman filter equations.
Exactly. Yeah.
So the concept is similar of like these, and then you still need the derivatives, but you're right. It's not. These are different equations.
Let me also turn the floor to the co-host. So Christian, Vasil, Narti, do you have questions that you would like to ask to Babak?
I actually do. Thank you, Babak, for this very interesting presentation. I was a little bit intrigued about these regions of, these scatter plots where you show your prediction, and they were a little bit off from the mean, and you said it was slide 31, I think. And if you update those, you will get a better result. My question is, do you have any interpretation of that deviation, that initial deviation? Does that give you some information about what is going on with your data, or just even a matter of uncertainty?
So that's a good question. So we are tuning, we are doing model updating, but a lot of times when we have a complex structure, your data tells you, for example, if you reduce, so here I want to, you see my predictions are gray. I want my F2 to come down, right? So if I tune my F2 to come down, my F3 will also come down, but that's bad. You see, they are pulling in different directions. So the model updating reaches a point when both of them are bad, based on the weights and based on the compromise. So the optimal value cannot do any better. So the rest can only be handled by accounting for modeling error. And a lot of times this data, whatever you update, the model, the data is pulling one parameter one way and the other way, and they are basically contradict one another. This is the case here. So when they pull them, then you can when you want to visualize, you visualize and you say, oh, this is not a good thing. I can quantify my, so again, the same thing that Mike was saying, these are a lot of these structures that I put into updating is after the observation. So I tried, so these are not online. I have spent times, like I did case 1, I had no clue I would do case 2 and 3 before I looked at these. So we looked at them and said, you know what, this is what we observed. This is the bias. How can we fine tune the structure to address that? And this wasn't, I didn't know, again, some of these you cannot, some of them you may be able to do that beforehand. Some of them you may not. You basically observe what you have done and then you say, this is not good enough. I can do it better. Does it make sense, Christian?
Makes sense. Yes, thank you so much.
I see that Eve has also raised his hand, and then Armin. Okay, so Eve, maybe you go first.
Yes, thank you very much for your really interesting presentation. For the very first case study that you presented, where you have some ambient frequencies and then some for higher shaking, right? And then you fit a line through these. Because you have mostly points in one region, I mean, in 2 regions, does this sort of favor to have a line through them? So would you trust the line that you update also for higher values? Or would you condition this on the amplitude that you measured already?
So it does weight, because you have more parameters here, the weight affects, but the good thing is all the points here are in 1 and they are not contradicting the other ones. So they don't give any information about the other ones. Now, if you want to make a prediction at ambient, you may be better off not to consider the structure of the line. But if you want to consider something that is not ambient, but yes, if I had, let's say, it's like any learning approach. If you can manually also, let me get a pen with a hypothetical. Let's say that you had a lot of points that provided a different line. And you had more points there. Let's say you had 1 million points under this line and you had just a few points here, then you would ignore these ones and fit the other line. But the shape of the line, I decided that. So I told the system that use a line. I know it should be quadratic because, you know, natural frequency and is the square root of the, but it was good enough. That's, where is the fit? Yeah, the fit is good. So it was good enough. The simpler the model, the better it is. But yes, the weight, the number of points affected. It didn't affect this one because they were all in agreement. They were not pulling in different opposite directions.
All right.
And Armin, I think you had also raised your hand. You have a question? Yeah.
Do you hear me?
Yes, yeah.
Hello, everyone. Thanks for a great presentation. I just have a quick question. In such problems, in inverse problems, I mean, how we can be ensured that the problem has a unique solution? For example, we might have some other local solutions. I want to know how you determine this.
So, I mean, you cannot force the problem to have a unique solution. If the problem, your data does not provide unique, it is not unique. You just have to have a good, like, let's go to a classical sampling or hierarchical sampling. So if you go and your data provides, is this a pen? Yes. So let's say you have 2 parameters, theta 1 and theta 2, and your data tells you this is one high probability area, this is another one. It is what it is. The data cannot, you need more data. That's what it says. So no unique, but you have to quantify both. So if you quantify just this one and show this one, it's bad. You have to say, oh, I have this and that. And there are techniques that you can get both of them.
Yeah,
both
great.
in sampling and both analytical.
Thank you.
No problem.
But may I ask, actually, I have a question which is mostly educational again, and a comment on virtual twins. The question is, let's say, in generally, when you want to apply the Bayesian inference, right? How is there any hints? How do you select your prior distribution in practice? So let's say, using an example among the ones that you have presented us, you have a bunch of parameters, and you say, okay, I assume a Gaussian distribution more or less, but are there any tricks inside there in order to tune it a little bit better and to provide better information in a probabilistic sense into your layers, into your onion layers?
Yep. So the prior is very important. So Vasilis, my comment is to be humble with your knowledge. Talk with engineers. So people who design the structures, they usually are the best resource. They are better than academics most of the time for the prior, because they designed, they made assumptions. Talk to them and then be humble about what you know. The more, if you make your prior very narrow, it becomes like a political problem. The more information you give, it doesn't affect the results. Indeed. So it's just prior, basically. So you want your prior to be, and that's the problem with classical Bayesian. The classical Bayesian, basically, it looks like a recursive. Assume that you have a recursive case, and then you give one data, and your prior gets narrower and narrower. The last few steps, it is what it is. Then it gets almost zero variance. But yeah, I don't have an answer that is systematic. I just tell you what. Systematic
is yes. Although in general, you can, let's say, kind of group it into classes. So let's say a building structure or a bridge structure or a wind turbine might have some classes. Let's say a cloud of possible. Let's say.
That's right. That's right. The more. So for example, the more mechanical system like.
Rotating
like wind turbines. Wind turbines, you have more knowledge. But
okay, and the comments, if I may, I mean, if we have some time on the general concept of a digital twin is, as you very well demonstrate from your first example, is that a digital twin is something much bigger than a model updating process, right? So it depends.
Yes.
So let's say when you want to establish a digital twin of a wind turbine or of a bridge or whatever, you have to take into account, among other stuff, your input space, right? This is something very important.
Yes. And what operations of the structure have you considered in your data? So always extrapolating is not very good.
Indeed. Thanks, Babak. I think we have a couple of more questions, Eleni.
Yes, we're slightly over time, so we'll take one last question, actually, because we should be prompt with our timing. Perhaps, or let's make it actually 3, if they can be short, because I see there's only 3 raised hands, so no reason to choose. I think Funchang has one question, so you could go next, and then Masood after that.
Yeah. Thanks, Professor Babak. Thanks for this interesting lecture. So I have a question. Like when you evaluate the model solution based on the joint distribution of the parameters, I'm wondering like how much computational efforts you have to spend on the model. And like I would expect when the model is more complicated, the computation efforts will be like increased a lot. And I'm wondering like if there's a way to account for that. And also like for the real-time model updating, like did you just for the model solution, did you just calculate once before you actually doing the model updating, or like you have to evaluate the model solution every time in the iteration process of the model updating? Not sure if that's...
So yeah, they are both related to computational efforts. There are, so I didn't talk about computational efforts here, but when things get very expensive, I think I mentioned this here, we just go after the map values. So what I'm updating is the mean and covariance. Mean and covariance have uncertainties, but then I don't care about that anymore because it's expensive. So I go after their most maximum posteriority, which is the most probable values. And that is very cheap, you have to still run the model, but you can do a local optimization. Basically based on the asymptotic approximation, you can also get the Hessian if you want. But what we do a quick optimization, which is faster because you still have to iterate. If you want to fully sample your space, that is super duper expensive. And that will take, that's not very feasible for some of them. It depends again on the application, but like Gibbs within Metropolis Hastings for multi-dimension and iterative within iterative. So if it's nonlinear, you have iterative. If it's recursive, it's another iteration on top of that. And if you do this adaptive, you have another iteration on that. So you have 3 loops of sampling. That's unfeasible. But good point. Yes, we just go after the map values, and we do asymptotic approximation.
Okay, that makes sense. Thanks.
I think Masoud, you are next. You would like to go with a short question if possible, then we take one last one from Zinyu.
Sure. Eleni and Christian, thank you for organizing this wonderful seminar by Babak. Babak, on the uniqueness question that you showed a domain of parameters with 2 probability of having, let's say, damage. At that point that we have 2 answers, can we use our engineering judgment or the designer's judgment, of course it is offline, to judge which set of answers are more feasible? Meaning that sometimes I have noticed that you might get very large stiffnesses that might not be feasible, or even negative values that can't be right.
Yeah, that's a very good point, and it loops back to what Vasilis was saying. So you can, if you change your prior, basically that can make it unique. But again, you have to make a loop back and make a judgment there to narrow one of them. So your engineering judgment is usually in the prior. You can change your prior, and then your non-unique problem can become unique. So you can loop back. You say, oh, if I don't make this judgment and I'm very humble and I make it very uniform and broad, I don't get unique. So I go back, do more education, talk with people, make a narrower prior, and then your problem potentially becomes unique. Potentially, not always, but.
Thank you.
Thank you, Masoud. Maybe then the last question from Zinyu. I know Zinyu is working on the same problem, so the floor is yours for the question.
Yeah, thanks very much for the very nice presentation, Professor Moaveni. I just have a quick question for the hierarchical Bayesian modeling part, since I'm also working on this area.
I know that we have a paper together.
Yeah, we have 2.
2 papers, yes.
Yeah, because basically what I do is just assign the hyperparameters for the model parameters, not the hyperparameters also for the model error part. As I say from your presentation, you also assign the hypermean for the model error part, and you assign it as a Gaussian distribution. I'm just wondering. Of course, it's good for the prediction. So I'm just wondering, can we assign another distribution for the model error?
Absolutely. Again, it goes back to Mike Todd's question. So the best, if you don't know anything, best is go with maximum entropy. Finite mean and variance, just go with the Gaussian. If you know that it is most likely to have a shape of log normal, assume that. Better. The more information you have, the more restrictive you can become. But this was working fine for us. But absolutely, you are correct. You can go and assume a different model for your distributions.
Yeah, but it poses difficulty to construct likelihood function if we assign, for example, exponential distribution or another truncated normal distribution.
Yeah, and then they have to be conjugate to it. So for the analytical, but they are solvable. They have to be numerical, very expensive. That's why we didn't do it. So
yeah. Okay, all right. Thank you.
Thank you very much. Maybe then, since we're over time. What we typically do before I give the floor back to Christian to close the seminar is ask you, Babak, to leave us with some closing statement or message you would like to pass on to this, what you presented.
I don't have a closing message. I think thank you. I want to thank you guys. This is a good initiative. I'm glad to be here. And the closing message is the model of the structure is always the model. And again, it's the first thing they taught me when I took model validation. All models are wrong. Some are useful. Just remember that one.
It's a good statement. So Christian, the floor is yours maybe to close and remind everyone of our next sessions.
Thank you, Eleni, and thank you, Dr. Moaveni. It's been a great presentation. We are all excited. You guys are all excited about this event, and we can't wait to be here in a month. So please do check out our website, MARS-SHM.com. And thank you all for being here. Have a great rest of your days or evenings or afternoons or nights. Bye-bye.
Thank you, everyone. Bye.
Thank you, everyone.